the security properties aren't going to get done, aren't going to be met, we can always go back, but like that's pretty much it, right?
And the blanking proposal was brought up, but I think
we're going to talk about that. If you want to do that, that's great. Just give us a 2-minute starter. So I'll run this thing.
Okay, so we need. Do we have anybody who's willing to be the Jabber Scribe? Jabber Scribe, somebody. We need some help chatting with the people on Jabber.
I can do that, except I'm not on Jabber.
No, it works for Nadeem then. What time is it supposed to start?
No, we're 2 minutes late.
Oh yeah. All right.
Is the Jabber chat the same as the one on the Meet Echo chat, or is that different?
And if there's any questions, ask them, bring them up to the microphone. Yeah, you can do it? Okay. All right, so we have a Jabber Scribe. And somebody for taking notes. Anybody willing to take notes? Write things down. Let's pass around these blue sheets while we get somebody willing to write down the notes. Anybody? Yeah, let's get those doors closed. We need a note taker. Note taker extraordinaires. Anybody welcome to that? Chris will do this? Okay, thank you, Chris, you're a lifesaver. All right, so Chris is the note taker.
Excellent. Okay, well, we're not going to do that because that's annoying. Yeah, so here's the note well. It's Monday. You might not have seen it that much. Basically, it says what you say and do at the mic is going to be recorded, video and in audio. If you have IPR, you need to disclose it. Act professionally. There's a bunch of documents you can read about if you want to get the details. You'll be sick of seeing this slide by the end of the week. So requests, we did a good job with those. We got a minute taker, Jabber Scribe. The blue sheets are in the process of just going around. That's your name and your affiliation. When you're at the microphone, please state your name and also keep it professional. Our agenda, which we hacked up real quick, basically is this administrivia, the interim recap, where we're just going to do kind of a quick summary. And we've got a bunch of architecture. Both documents have been revised. So we're going to talk about some changes that were made to the architecture document. I think it's outstanding. And then we've got a bunch of presentations about the guts of the documents of the protocol, TreeCam and double join, authentication, handshake encryption and efficiency considerations, and some message protection stuff. We'll note that the person who is going to present the message protection is currently doesn't have power in his building in France. So we may have to see what to do about that. So that may fall off, but we have another session on Thursday, so it may go there, but we'll see what happens. And then we might have some updates on Thursday. If we get everything done early, we probably will cancel the Thursday session, but we'll see. All right, so first up is our quick riff from our chairs here.
Right, so we had a great interim meeting. It went pretty well. We had quite a few people working on the documents who showed up. We had several discussions here that will, these presentations that are going to happen today are going to kind of go over and summarize. We had discussions about double joins and proposal about blanking entries of the tree was introduced and debated. We had a discussion about art versus TreeCam, and eventually settled on going with TreeCam as the main construction, with the caveat that depending on the formal analysis, if it turns out that TreeCam does have some larger deficiencies that are not known now, that we may be able to roll it back. There was some additional discussion about message protection, in particular about AES versus AES SIV. This is something that we sort of tabled and we didn't resolve at the interim as well. There's also some discussion about authentication, and we'll recap this, I guess, in the presentation today. And yeah, so some other updates from there. We planned to go to the hackathon and have attempt to do some level of interop, and that'll be discussed as well here today. So that's basically the summary of the interim. And yeah, a bunch of ideas that were brought up, but the notes are available.
I was just going to say that, Richard, did you want to say anything about the hackathon before we go on, or is that in part of your 3 things in your bombs and slides?
So yeah, we did some work at the hackathon. We had 2 implementations there, the Melissa one from the Wire folks and my MLSPP C++ one. We unfortunately had a crypto interop issue in that I had it implemented with P256 and Raphael had implemented with Curve 25519. And I think neither of us got crypto agility working in time, but we managed to get some basic level of interop. We have now a common set of test vectors for the tree math, so just how you navigate left, right, parent, sibling within an implementation. We now have a common set of test vectors that both stacks pass on. So we've begun our journey toward interop with the first baby step.
I mean, I look at the crypto problem as a good thing in one way, because the next third person that shows up is going to be able to talk to one of the 2 of you, right? Because there's really only 2 choices of how we're supposed to pick, right?
That's right.
Okay, great. All right, thanks a lot. Ahmad, you're up. It's 1 slide, but still, we'll give you the clicker.
I got to use this.
All right.
Okay, I don't think I will use the 15 minutes for this, but yeah, I want to cover the open issues architecture doc. First, these 2 points are actually clarification more than open issues. Some people still confuse what the purpose of the architecture doc. Why do we have 2 docs? Is it competing docs with the protocol doc or not? So our intention was to have a separate independent doc to define the function and security requirements for the protocol. And this is completely separate from the protocol. It's not competing, it's just complementary. And we will keep, of course, changing this and updating it as we need. In fact, the third bullet point here is one of these changes we are proposing after we implement the protocol. Deniability. So yes, deniability is still one of MLS goals. It's drafted in the current doc as optional. Still an argument to have it as required or optional, so this is still open for debate. To clarify deniability, what we meant by deniability here is peer deniability, not server deniability. So peers cannot correlate messages with the long-term identity keys. DS trust, or delivery service trust. So the current draft mentions that delivery service should only store information needed to deliver messages. However, while implementing MLS, there are some scenarios that Richard and Rafael are gonna cover later. It makes more sense and more efficient to store some public group state in the delivery service. So the proposal here to add this as an optional mode, like to store optional information about or public group state information to the server if it makes sense, more efficient. So is it safe to do so? And is it okay to add this to architecture draft? Any question? If not, I'll just.
Oh, no, I was just going to say we did get some reviews, and so the more you read it, the more we provide comments, the more we'll adjust them. So please comment and review on list. And there is a GitHub repo as well, so if you want to save some work for the author, pull requests are accepted. Okay. Cool. All right, Richard, I think you are next. That's the big one. I called it stuff. That is a good question. recap. So the tree came in double joint stuff.
Okay, yes.
So it's this one? That one, okay.
Very good. There's no preview on the screen here.
Blink, that's why.
Yeah, sorry everyone. I just sort of jammed all my slides for 3 different slots into one big deck. So we'll be piecing through this as we go. So wanted to recap real briefly where we ended up after the interim. We presented a sketch of this at the interim, and then I integrated that into the draft in between the interim and now. And so I was going to kind of recap where the draft is now, so people kind of understand what the approach is, so this will kind of set the stage for some efficiency considerations that Raphael will bring up in just a second. So it's something that we need to emphasize in the doc a little more heavily is this idea of what I've been calling the tree invariance. So you'll recall that the way we get efficiency for big groups in MLS is we arrange the keying material, the crypto state that the participants hold into a tree, where there are DH key pairs at each node in the tree. And the goal of the protocol that we use to manage the tree is to maintain this invariant, that the private key for a node, a circle here, is only known to the descendants of that node, the cone underneath that node in the tree. And what that enables us to do is that when we want to send a secret value to a part of the tree, to that orange area there, we can use the key at that point in the tree to encrypt to all the leaves at beneath that point in the tree. We've had for a little while in the protocol this idea of a double join. The phrase comes up because it first arose when we were talking about adding people to the group. What we call a double join is when we have a violation of this invariant, a point in the protocol where the private key for that node in the tree is known to someone, to the holder of a leaf who's not under that node in the tree. So someone who shouldn't have it according to this tree invariant. So these double joins make the tree more difficult to manage. The invariant, kind of gives us a convenient mapping between points in the tree and subgroups of the overall group. And so if we have this double join around, then it makes it more complicated to reason about, because you have to track who's double joined to a node in addition to who should have the private key according to the tree invariance. So we've been trying to eliminate these double joins to clean up the protocol and make it simpler to reason about who has which keys. The trade-off is, so let me just completely with double joins. So prior to draft 02, which we published for this meeting, the add and remove operations resulted in double joins. So this is a kind of modern art depiction of an add operation. So the intuition here is that this node over here at the left is adding a new member on the right. And in earlier versions, that the member sending the add would set values for all the nodes above the new node, the new member in the tree. And what that implies is that the sender of the add gets double joined to all of these nodes above the new member in the tree, because he's not that new member, but he still has access to those keys that he shouldn't have access to. Right? Because you can't set a value, you can't set a private key without having access to the private key yourself. So up in the earlier versions of the draft, we had these double joins, and at the interim proposed a way to get rid of this, which is basically just don't set things you shouldn't have access to. So the solution to not having double joins is to, in the add case here, instead of setting all of these nodes above the new node, you just add that new node using a key pair that he's published that the new member has and is not accessible to the entity doing the add. And for all these other nodes above that point in the tree, you just leave them blank and you don't set them. Now, that can be made to work in a fairly straightforward manner. You just kind of take all the algorithms we had for doing adds and removes and updates before, and wherever you were going to encrypt to a node, you instead encrypt to what I've called the resolution of that node. So in this scenario here, this node is updating and it needs to send out private values for these. It needs to encrypt the private value for this node to this node, and the private value for the root to this node. But this node is empty, And so we flow through in this resolution algorithm to the populated children of that node. So this one here and this leaf here. And so the ultimate encryption you get in the messages is this encryption of this value to this node and the encryption of this value to this node and this node. So instead of having 2 encryptions, you have 3, which hints at one of the impending problem here, which is that resolution inherently involves more encryptions than encryptions if you had a populated tree. And so that's the problem we're going to run into in a minute. Yeah, Dan.
Yeah, this is DKG. So I'm a little confused by this example view. How do you get into the state with this example view where the root node is known, but one of the children is not?
Let me fast forward.
Okay.
Let me get to the next slide because there's 2 scenarios that create incomplete trees. So the way to think about it is we have adds, removes, and updates. Let's say adds, updates, and removes. Adds create empty spots in the tree in this way. Removes create empty spots in the tree by, by removing the direct path from the removed node, which I'll illustrate in a second. And then updates undo, they heal the tree by, in this case, if the root node had been blank, then this update would have reset the root node. Yeah, so this is what a remove looks like. When you remove this third node here, you blank out its path to the root. It turns out that the content of the root node in what we've got so far doesn't really matter because you use the content of the root node as a shared secret and never really use it again. When you're encrypting to the group, you're using the symmetric secret that you've derived there, not the public key that's at the root. Yeah.
I mean, yes, I agree with that statement, but Eric Scola, but if I were to encrypt the entire tree, I mean, imagine a pristine, perfect tree, then I would in fact encipher the root node, correct? I would encipher the public key of the root node.
There is not an instance in the protocol right now where you would need to encipher to the root node. I mean, yeah. So in the update, right, but the way those symmetric keys get used is they're fed into a key schedule, in their KDF together with the history. You don't use the content of the root node itself. It's used
Right.
only ephemerally to generate the epoxy code.
Because what you're going to claim is that all the other cases require encryption to some subset of the tree.
Subset of the tree. Yeah.
Seems like there might be times when you might need to.
It could be, but in any case, this is how you end up with a blank at the root.
It's a funny. It's just worth noting that like it's I know Karthik had this vision of like it's trees all the way down, and having that asymmetry where even though the root node is populated, you're not going to encrypt it. Like totally destroys this trees all the way down.
Yeah. In any case, DKG, going back to your question, this is how you end up with a blank root node. If then, say the right-hand node sent an update that replaced all the nodes in its direct path, then you would end up resetting the root node to a group value that's known to the whole group. Because that update, it would send this value to this node, this value to this node, and then it would send the new value for the root to the populated tree heads under that by resolution. Yeah.
Yeah, the slide that DKG was concerned about had a nice color scheme that would show this.
Yeah, similar idea. One of the interesting things, and this gets us, this is I think my last slide, and this is really makes the inefficiency point really clear. One of the nice things about this, we've had a stub in the draft for an initialization operation for a while. Initialization of a new group with n members is inherently going to be an order n operation because you have to do something for each of those members. And what's nice about this, the idea of having an incomplete blank tree is that when you add, so say you start with a one-member group here. When you add the first participant, what we said earlier that the add just adds the leaf and doesn't add anything above the leaf. And so if you just do that repeatedly, you end up with this tree that has only the leaves initialized, which is very natural, very simple to describe initialization operation. The problem with that is that now you've created this tree where any operation you do, well, if you want to send an update to reset the root, you have to encrypt individually to each of these leaves. So the update you send is linear. And so if you initialize a group with 10,000 members, you have to do 10,000 individual encryptions. You're not getting any benefit at all from the tree structure because you haven't set anything up, because that would have violated the tree invariant. So we end up in this case where we have a very clean semantic because we've removed all the double joins, but we have very low efficiency in this initialization state. Because of that increased semantic clarity. And so we've kind of gone all the way from the semantic ambiguity but high efficiency end of the spectrum to the high semantic clarity and terrible efficiency end of the spectrum. And so I think Raphael has some thoughts on how some intermediate points we might explore. I will observe that, so this is kind of the worst case for efficiency. If you have a tree that's reasonably full, I mean, kind of based on the empirical, some simulation work that Raphael and I have done, if you have a tree that's reasonably full, then removes and adds will cause some blank nodes to appear, but they don't have, you don't stray far from log. And I think I sent some notes to the list with simulation results. Yeah.
So I feel like you must somehow lost me here. So I certainly agree that this state is like really terrible, but as far as I know, all the protocols that anybody's described have a linear setup phase.
Yeah.
So this first thing I'm confused by.
Yeah, the question is how bad a hangover is there from the linear setup phase? So the initial creation of the group has to be linear. The question is the next thing you do log, or is it linear, or is it half linear, or what have you?
Right. So
actually, I think I have to do one more slide. Yeah. So if you do this what I said, you have this like warm up phase. So the blue line at the bottom, which you can't see because it's next to the axis, is log n. And so if you had a full tree and you had the double joins, the first operation would be linear size, and then everything else would be log size. And if you don't do that and you're just doing random operations, you kind of gradually converge from linear down to log.
So let me just see if I understand the intuition here, which is that, can you go back? So the first person to do an update basically fills in his direct path.
Yes.
And so then updates in that part of the tree are somewhat more efficient than they were before. And then gradually more and more of the tree gets filled in, and then updates get faster. So is that the right
Yeah,
intuition?
that's exactly right. Yeah.
Right. Okay. Huh.
Yeah, and actually the way you do this, if you're going to do it properly, you'd actually have an L-shaped fill in here, because the creator of the group can of course send an update that will go ahead and make things more efficient than they yeah, exactly.
Ben Kate, well, don't you also expect a lot of the group members to be sending an update right away?
Well, in practice, yeah, you would hope that like as people join the group, as people like come online and realize they've been added, they would send an update. But we're designing for asynchronous operation here, and so if half the group never comes online, then their half of the tree will never get populated. So I think Raphael has some notes on some possible alternatives here.
This one? No, the other one. This one. Yes. Yeah. This one.
Yes, that looks better. Yeah, so the clear advantage of having this blanking mechanism is that you can effectively evict someone from a group by deleting all the nodes in their direct path. But as Richard just said, that is not adding to the overall efficiency. So the idea was, couldn't we do something about it in general and specifically for the init, which is completely inefficient at this point? So just to look at it from another perspective, if you blank something, there's only one rule. You just need to get everybody to agree on which nodes have to be blanked, and that's it. The next step only comes when you resolve a node, when you prepare an update, for example. but that is in phase 2. So as I said, you can evict someone effectively from a group, but you also puncture the tree, and that decreases efficiency. So the idea was that maybe there could be the opposite operation of a blank, which would be a set, where one participant of the group would simply set the node secret of an arbitrary node. And so we looked into it a bit. It is not generally super useful. So the scope of this would be only to increase the efficiency. And because all of the security guarantees we have achieved with blanking already. So there's more than one rule with this one, because if you set a secret of a node, you need to tell that secret to the children of a node or to the resolution of the children if the children are blanked. And this effectively creates a double join, the very thing we just wanted to get rid of. So that means that whoever set that node knows that secret until the node gets overwritten by an update. But if that doesn't happen and you want to evict the setter of the node, you effectively need to blank this node in addition to the direct path of the setter. The upside could be that this heals the tree and makes it more efficient. Downside is clearly the double joins. So yeah, this is a slightly different definition, but Richard covered that one already actually. So double join is what we have when someone knows the secret to a node that is not in their direct path. So if we were to allow double joins, we would have to track all of them to know exactly which member has the secret to which node. Right now, we implicitly assume that every member has the secret in the nodes of their direct path, so there is no need to store that anywhere. But if they know the secret of nodes outside of that, we would have to do some bookkeeping. So there would have to be some structure that contains that information. That's what we would call the book. And this book would have to be passed to new members or new devices in a multi-device context. And what is also important is that everybody has the same view on the book, because members might have the incentive to lie about certain entries. So for example, if I invite someone to a group, I might be tempted to not tell them which nodes I have double joined, so that I could maliciously still be part of the tree even if someone evicted me. So for that, we would need a mechanism to make sure everybody has the same view on a book. And while the naive approach would be to make the book part of the group state, which right now becomes part of the key schedule. So we could, thanks to the key confirmation mechanism, detect any lies in the book immediately. So this is a naive yet flexible idea of what a book could look like. So for every node, there's an entry which might have 0 to many owners. And there are many entries in a book, depending on how many nodes have a double join. Of course, there could be more efficient representations in memory of a book if you accept certain constraints on how many owners there can be or where the nodes are in the tree.
And Raphael, this is Richard Barnes. Just to be clear, we need to have this information available and serializable so that you can tell it to someone who's joining the group. Because if that member needs to evict someone who's double joined, he needs to also tell everyone to blank out that node. Or know, actually when he's processing a remove, he needs to know to blank out any nodes to which that the member being evicted is double joined.
Almost, yeah.
It's a terrible idea outside of one limited case.
Yeah. I mean, it was worth investigating, or at least presenting the results so that we don't do that twice. But I mean, this is exactly why it's a terrible idea. Maybe you suspected that already. So if P is the node that was previously blank and we want to set a secret in there, then we would have to tell that secret to the left and the right children, or the resolution of these nodes. And so specifically when we set something and we suppose that the left children was already double joined by, say, Alice, and now Alice previously only knew the secret of L. If we chem the secret of P to L, then Alice has effectively also double joined P. And all we did was basically to just set P. So this increased the number of double joins for Alice, which is certainly not nice. This could be alleviated by the fact that instead of chemming this to L and R directly, if those nodes are double joined, we could do some sort of a resolution there where we assume that any double joined node is in fact to be treated like a blank node. And in that case, basically we wouldn't chem to L, but to the children of L, as long as they're not double joined. And that would prevent Alice from knowing the secret, the new secret of P. But it is quite expensive. And it doesn't really help because if we do an update, which, as Richard pointed out earlier today, could be seen as a number of sets, really. Now the problem is that Alice initially double joined L, she gets to know the secret of P, and because in an update we hash up the secret all the way to the root, so Alice has now double joined all the nodes from L to the root. So yeah, worst factor would be log of n in this case. So it gets messy, yeah. So aside from that, there seems to be an invariant where if you accept that the book would increase in size, the operation cost would go down and vice versa, basically. But a book that is increasing only means that you have postponed some of the work, because it means that if you want to evict members at some point, you will have to do a lot of blanking because of all of the entries in the book, and then actually everything becomes very expensive again. So if anything, you could buy time with this. So there is one edge case, as Richard said, and this is actually what triggered this whole research, and that's the image edge case where you start with a completely linear model, and the cost is in O of n. It does converge rather quickly. So Richard did that simulation. I tried it on my end. I think this is the graph. So this is very thin on this monitor. How do you activate the dot here? So this means is that 1,000 is the number of people in the group. And so the very first update has a cost of exactly 1,000 because the resolution will be 1,000. So as people come online, and you expect them to actually come online rather quickly, typically, I mean, it is asynchronous, but some people are going to be online and they will immediately start to do an update. So this is going to actually decrease very quickly. I don't know if you can see this blue line here. So this is the average copath lengths, the average from all members, basically. And there is a worst case and a best case. So roughly after, it's hard to tell from this graph, but after less than 50 updates, you're already below 100 Diffie-Hellman operations. So this is good in general. The problem is that the first 30, 40 members who come online, they have an insane amount of calculation to do.
Sorry, there was a graph that was up earlier that showed a very different picture about convergence. And I'm wondering if you could just explain what the x-axis is here that differed from what the x-axis was on the previous graph.
Right, I think they're fairly similar in the sense that in the previous graph, it was a timeline and it was interactive. of people who joined doing an update and also doing other operations. Whereas here, I'm assuming that people only come online at some point and will do an update.
So you don't have, so basically you don't have any removes.
Yeah, that's correct.
So that's
this
why
is
that
a
doesn't
pure
come back
thing.
up.
Yeah, exactly. So the effort never goes up again. This is not. Yeah.
I think there's two things. Yeah, there's no adds or removes here, and I think there's many more time steps here. So mine was the first 50 or so time steps of the group, and he's covering the first 1,000 for the whole group to update. So you're seeing some horizontal compression in this case.
Right. So I mean, it converges all the way down to this purple line, which is log n. So this is actually a very nice scale to see the difference between n up here and log n down here. And that is only for a group of 1,000 members. So with 10,000 or 50,000, it's even more dramatic. We all know that, but it's always impressive when you see it. So the one idea that occurred to me is that potentially it could be a good idea to increase the efficiency by warming up the top of the tree. So what does that mean? If the creator was to pre-calculate some of the node secrets and share the public keys with everybody, and effectively double joining all the nodes in the top of the tree, that could maybe have a very good impact on the overall efficiency. Because if we look at this graph again, so what we see is that the problem is really only here in the beginning. Once we're like here, we don't care about the rest because we're very close to the log n line, and there's nothing to improve here really. So we pre-populate the top of the tree, meaning the creator of the group generates secrets and derives private and public keys and makes those available to everybody who's invited in a group. And it is most effective if that is done at the top of the tree. It could be done anywhere, because just like you can blank a node anywhere, you can also set a node anywhere, but it is most efficient at the top. That's where you reach most of the leaves that are underneath. And so a tree is composed of levels horizontally. And so with every new level that is being populated, you basically divide the cost of the first update by 2. So this decreases rather quickly. So an example in numbers, we take the group of 1,000 members again. We take the top 3% of the nodes in the tree. So there's like 30 nodes in this case that are pre-populated. So this is still fairly quick because we only pre-populate 3%. So for the creator, this is really not very expensive to do. And it's still linear in theory, but it is fairly quick. And so that gives us a completely new picture where the scale has changed quite a bit. So the first update now is not 1,000, it starts at 70, and then it converges again in the same fashion as the other one, except that you don't have these high numbers anymore. And so this is a comparison chart between the two. So that the purple one is the initial one that started at 1,000. This one starts at 70. And then they basically very quickly not only converge, but actually become identical. Because the effect of the pre-population of the top of the tree wears off rapidly as updates will overwrite all of that. So that looks good, but we still have a double join situation as such. So there is some sort of a cleaning mechanism. So as people come online and do updates, they will overwrite the tree. So we still have this proliferation effect that we saw earlier when you have a double join node and that happens to be in the co-path of an update. But the big difference here is that, first of all, all of the nodes are only double joined by one person, which is the creator. And so anything above a double joined node is also already double joined. So this, this particular problem has no effect here. And what happens is that as people do updates, one level at a time, the double joins are going to vanish basically until you really only have the top of the tree that is double joined, and then also that goes away. And so if you warmed up k levels of the tree, it would take roughly 2 to the k plus 2 updates to do this cleaning. And in the example before, we had 5 levels. So 2 to the k plus 2 is 128 in this case, in a group of 1,000. So roughly when a bit more than 10% of the people have come online and done an update, which they're supposed to do, the tree is completely clean again and reasonably populated. If they don't, for some reason, you can still evict the creator of the group by blanking whatever nodes that are left and are double joined. So you would also need some bookkeeping that need to be passed, but it could be much more simple than what we saw earlier. Yeah, question, Baker?
Yeah. How much simpler does life get if we just assume the creator is special and can never be evicted?
It gets cheaper if you don't blank the top of the tree. So, and while you don't have to do the bookkeeping,
right,
depends on how we're going to do that exactly.
I mean, I guess I'm just saying, like, there certainly are, like, you know, there are messaging systems which basically have the structure like you sort of assume the creator is special, and I'm just wondering if you were willing to tolerate, you know, if you're willing to tolerate that restriction, like, would that be a very substantial gain that we would be willing to pay?
Yeah, I mean, that is definitely a good observation, because most systems where you have a creator, you'd assume it's some sort of administrator or moderator or whatever, and those rarely get evicted from a group. So the cost you would pay right now in such a situation would only be the bookkeeping. If there's only one person who can double join, then you can condense the bookkeeping to something that is bytes to kilobytes, maybe in larger groups. And that just needs to be passed around. So on the payload size, it's not really a pain. So the cost seems quite reasonable for still being able to evict even the creator.
Yeah, the upshot, if you want to do double join only at init time, is that you need to carry around 1 bit. Well, so if you want double join only at init time and you want to be able to evict the creator, then you need to have 1 bit per node in the tree that indicates whether the creator is still double joined to that node. And the cost, until you try and remove the creator, is only that. And then when you try to remove the creator, you have you take then the cost of removing all the nodes from the tree that the creator is still double joined to, which could, you know, drop you back into a linear state.
I mean, I guess to cut to the chase, right? It seems like the recommendation you're edging towards is that we do that. Namely, the creator create the tree in a populated state with the bookkeeping to allow the creator to get kicked out if you absolutely have to. Is that what you're basically shooting for?
Yes.
Okay. Yeah. I mean, that sounds like a good plan.
Sorry, and just to be super clear, if you allow the creator to be double joined and never to be evicted, then you don't have to keep any extra state at all.
Yeah, that would be correct. Yeah. Right, quick summary. So generally setting nodes is expensive and doesn't really do any good, but warming up the top of the tree certainly can increase efficiency. So this whole thing was really only about efficiency so far. The whole security aspects are only tied to how well the bookkeeping works. So that we would have to make sure that the bookkeeping is reasonably secure. But it's nice for once to have a discussion only about efficiency. Yeah. Any questions?
So I think to kind of continue where Ecker was going with this, I think thinking of this as warming up the top is probably probably not worthwhile. If we're going to take the bit of state, if we're going to have the bit of state around, you might as well just initialize the whole tree and get max efficiency.
Yeah, it would be interesting to do some simulations because, so again, if we go back to this graph, so the situation comes, more than bearable after 20% or whatever you assume to be a good situation. So if you pre-populate the whole tree, I mean, yeah, you converge more quickly towards the log n line here, but that's really it. And you would put a lot more load on the creator. So right now the creator only does 3%. It could be a different number, of course, but doing 100% in large trees can be much more expensive because you derive the keys.
A couple of clarifications. If you pre-populate the whole tree, then you are never not log n. So the first update that someone sends is immediately efficient. Like it's
Right.
immediately log n. So there's no warm up period if you pre-populate the tree. And the second thing, which John Milliken convinced me of a little while back, is that you don't actually have to do any additional Diffie-Hellman operations because you're already establishing a secret key with each of the new participants. It's just additional stuff you shove
Okay.
into that blob.
I mean, that's something we can certainly look into, yeah.
So this is Daniel Kahn Gilmore. I just wanted to observe that we're having this discussion based on the idea that what we care about is a large initial group and that not every group is large initially, right?
Yes, absolutely. That's
if
clearly
they're
an
going to
edge
be,
case.
yeah, if they're going to be ads that like a large number of ads that happen later, then this analysis doesn't necessarily apply to that case.
Yeah, absolutely. I mean, if you start with a small group, and probably most groups will start that way, where you don't have a fixed set of participants in the beginning, then, but the big difference there is that the tree will already, be populated with a small group of people. So it will still be expensive to add a large chunk of people, but it's going to be much better than linear.
It's not just expensive to add a large chunk of people, it's expensive to operate the group if the large chunk is added post-creation, right? If we're talking about special case and creation.
That's what I meant. Yeah, adding them is still cheap, but then doing updates is where it gets expensive. Yeah, agreed. I mean, we could probably do some simulations there as well, see how bad it really is. My gut feeling right now would be that it is still a lot better than the linear init as such.
Is it the case that doing updates is the only expensive thing, or is actually sending a message more expensive?
So no, I mean, the message is only encrypted once under one key that everybody should have. So
with blanks?
Yes,
Okay.
blanks as well. Yeah, that doesn't change.
Sending messages is always constant time because you've established a symmetric key that everyone has. It's only, so ads are easy in any case because you're just, ads get more-ish expensive. Oh no, actually in the latest one, no, you just ratchet forward, so you don't actually have to send a new entropy to the group. And you just send entropy to the new member. It's updates and removes that get expensive because you have to send information to a subset of the tree.
I think I'm like just about talking about numbers. If I have to bias between, first of all, if I have to bias between like upfront work at create time versus work by people once the tree's created, I think I'd prefer to bias for upfront work at create time because if you're creating a 10,000 person group, like first of all, you have to do like a crap ton of work just to get that to work. I mean, like, like just selecting all the people is gonna be super expensive. And so like if you have to burn like if that operation takes seconds, nobody really cares, but I really don't want to be the case that when I join the 10,000 person group, then like I got to spin my CPU for a while to like just do anything at all. So I think I tend to bias that way in terms of efficiency.
To pre-populate the whole tree, just
yeah, exactly. Plus, it's like simpler to think about. I'm like dumb, so it's like easier. As I understand it, that in the case where the tree gradually grows, it's like not actually that efficient to build the tree that way, but it's spaced out over time, so you kind of don't notice. Is that an accurate way of thinking about it? Like in the version where you like add people one at a time, that's actually not a particularly efficient way to do it, but it's like, but it's like nobody notices because like you had like one guy and then another guy, right? Yeah, yeah, right. So that seems like actually a fine case.
The use case that I was worried about was if we're talking about like say company size groups, is that the admin sets one up which is just like, you know, small tests, make sure the group works. Now it's working. Now we're going to turn around and add, you know, the entire division because now we know that the group is working and now we add the entire division. And if that suddenly becomes expensive, then that's kind of a weird, like the UI becomes weird.
Yeah, that's a good point. Yeah. So that could lead to a recommendation as to the user experience.
So I haven't thought about the tree math well enough, but like if you need to do, if you have a existing small tree and then you need to do a bulk add of a crap ton of people, is there an efficient algorithm for that? It is not, there's more efficient than I'm guessing there is.
Well, I mean, what we considered with the setting mechanism is that you could pre-populate the direct path of each and every one of the people you add. The problem is then the double join. So you end up again with a tree that has a lot of double joins. So
right.
That would make it efficient as such.
Right. I mean, DKG's example, right? I mean, in DKG's example, that person is the admin, and so double joining them is like it's like, you know, if that person gets fired, you just deal with it. I think so. I guess I'm sort of like generally like, I mean, I sort of have in my head that there's sort of two main environments here. One is basically enterprise cases, in which case you have like a lot of people, but you do a lot of bulk adding, and that person's an admin, and just like when they get fired, you deal with it. And the other is sort of like spontaneous groups that grow gradually, and those don't need massive joins. But maybe the case is that, you know, I'm the founder, but then I'm like an awful jerk and I get kicked out, and I do have to get kick outable. But that doesn't have this weird property of like, you know, one mass setup, right?
Right. I mean, if we assume that the creator should, you know, never be evicted, or if we want to evict the creator, it's allowed to be super expensive, then we can actually calculate the direct path for the people we add. I think that could work if you add a ton of people after the creation, but we'll have to look into the details.
I think that would be the simplification I'd propose, unless somebody thinks that like there's an important case it doesn't work. To be honest, I've like sat through a lot of these presentations, and I spent more time. I'm sure I spent more time than average thinking at the tree math here. And like, nevertheless, I spend the first 10 minutes being like, co-path and resolution. Like my head like hurts. And it's like the more we can make this not complicated for people, like unless like there's like a lot of gain, I think the better.
Richard, do you have a comment? No.
So aside from simplicity for poor implementers whose heads are spinning, it may also be that the model for the users about what is an expensive group to operate in versus what is like not an expensive group to operate in might be like, if the efficiency is unpredictable and people are like, I don't know why this group is so expensive to operate. And the trade-off is between that or a design where we say, yes, some groups have admins and admins are expensive to evict. Like that's a very clear and predictable behavior, and that might turn out to be easier just to manage in terms of setting expectations for the users.
Right, yeah. I mean, later on, we're going to talk about efficiency more in general, so probably we'll connect to that again. Yeah.
So I guess I'm trying to figure out what the action item is for the spec here.
Well, I think Ecker's idea to basically extend the warming up to a situation where you add a bunch of people after creation, that would be interesting to see if that works as such by pre-populating their direct path and what the efficiency is there. And if we come to the conclusion that that does well, then yeah, we should simply add both things to the spec.
I think I might propose we do this in kind of two tranches. I think we should do init first because we've had a stub there. I would love to assign you the action item to write a PR that does init and with this. And then I think along with that, in that first tranche, is adding a flag to the tree node struct to indicate that a node is tainted, it's double joined.
Yeah.
And I think we can figure out the details on this, but you need the flag there. So that's kind of the first tranche. And then I think the second tranche you might consider is effectively a batch add function where you can introduce new tainted nodes. I think the normal one-off add should continue to be free of double joins, but we might consider a batch add that can add a bunch of people at once that's effectively the same as init in terms of how it taints the tree. Yeah, right. So that's why I paused and made noises about figuring out the details. Is because the critical thing is that the participants in the group need to know which participants, when those participants are evicted, do they need to delete all the tainted nodes, right? So in the init case, it's the creator. But in the batch add, where you might have other administrators around, if one of those administrators is evicted, you might have to blow away the tainted nodes as well. So that seems a little more complicated, but I think we can discuss that on the list. So yeah, I think let's do init with full tree warm up, and then figure out this batch add thing. Because I think the semantic is clear
agree
in the
on
first
that.
case.
Yeah.
Ben Kaduk, how much different or how much more work would it be if instead of trying to do this batch add, we just said, I'm going to do a new init for a new tree with everybody that I want?
Yeah, the thought had crossed my mind. I guess it depends on how many people are in the tree already.
Like the ratio of existing to being added people.
And also, I mean, you destroy everybody's local state by doing that in a way, which at first sounds very dramatic. I'm not sure if there are actual bad consequences coming from it, but yeah. Short answer, I don't really know. Yeah.
Marko Zahorski, I'm trying to get my mind around how the bulk adds affect the shape of the tree. So if a member does a bulk add of many new members, do they all get added to the same part of the tree, or do they get distributed across the entire width of the tree?
So right now they get added to the next free spot in the tree, basically to the right.
So does that lead to unbalanced trees if,
I mean, trees are not guaranteed to be balanced anyway. They're supposed to be left balanced, but now that you can remove people and blank their path, they're punctured anyway. So trees really have really changed in shape with blanking quite a bit, because you can think of them as a collection of subtrees to some extent, but
so can they get quite badly unbalanced if there's a bulk update in one part of the tree?
If on the left side of the tree you have a lot of blank nodes, then yes. Otherwise, it just grows the tree. They don't get really unbalanced. The only thing is that they miss a lot of inner nodes. So that's why it becomes inefficient. There is, however, one proposal on the mailing list right now, which I think makes a lot of sense. And that is to add people into the spots that have been blanked previously, simply to make the tree look nicer again.
So back to the bulk add, I like to think of the bulk add as tree merge operation. Like if you add the new people to a separate tree, you can find a way in the tree math to merge the two trees. I'm pretty sure, I think we might find a way to merge trees. I don't know yet.
Okay. Yeah. Make a proposal, Imad.
I think that will be an excellent topic for the next session of our graph theory seminar.
Okay. If there are no further questions, I guess we can move to the next one.
That's Richard. It's authentication. So Richard and routine. Yes.
All right. This has no trees in it.
That's one?
Yeah, that one. So this is kind of a recap of kind of like with the blanking stuff of stuff where we had an initial proposal at the interim. and we went off and implemented some stuff after the interim, between the interim and now this is a quick recap of what we did. So in the version we published before the interim, I had ginned up an authentication mechanism. Now, when I say authentication, this is how do we ensure that all the participants of the group have a consistent view of the public keys and identities of the members of the group, and how do they use that information to authenticate handshake messages as they come in. So in the version before the interim, I had ginned up a scheme based on some group authentication work in the literature, a scheme from Jonathan Katz and Moti Young, that basically folded a bunch of stuff into the key schedule that ensured that if any two members of the group had a different view of the roster of the group, where the roster is the list of identities and public keys for members of the group. If any two entities had different views of the roster, then they'd arrive at different group keys. This is great. So that the confidentiality keys are tied to the consistent view of the group state. So you have a nice correlation there. The thing that someone observed at the interim is, yeah, that's great, but you never have the participants never realize they have different keys until messages don't decrypt. So the suggestion that Cass Kramer has made at the interim was to have some explicit key confirmation as part of this. And so that is the addition that was made in the latest version of the draft. So in draft 02, we now have a key confirmation MAC. So you basically process this handshake message to update your group state to get a new group key for this new epoch. And then you use that new group key to compute a MAC over the handshake message to verify that you've gotten the same thing as the sender. So now by the time you're finished processing a handshake message, you know that if that processing succeeds, if the MAC passes, then you know that you have the same view of the group state that the sender did. So now, transitively across the group should have the same view. The only real question that came up, can you fix the alignment there? The only real question that came up in the discussion of this, which was admittedly a little rushed because it came in right before the draft deadline, was whether to have this confirmation be a MAC or to just derive something off the key schedule. So I made two PRs. The one of them got merged. I forget which is which. One of them got merged. The other is still open. The observation here is, in TLS, following TLS's pattern, we derive the key that you use for the MAC off of the key schedule. But the key schedule, this derived secret operation, already folds in the group state, which includes a hash of the handshake message that you just processed. So the group state and the message you just processed are all included in the derivation of this confirmation key. So in principle, I think, without having built a Tamarind model of this, I think that if you just publish that group key, that confirmation key in the handshake message, and everyone checks that they got the same confirmation key, that's sufficient. It proves the same thing that you would get as using that thing in a MAC to MAC over the handshake message. Now, what actually landed in the draft is you take that confirmation key and you use it to compute a MAC over the handshake message. Which is very much parallel to what TLS does in terms of doing its finished MAC to do the confirmation there. So the challenge here is that the reason this seems like kind of useless is that this derives HKDF extract and the derived secret operations are HKDF, which is based on HMAC to start with. So what we've done here is take a secret, use it with HMAC to derive the confirmation key, and use it with HMAC again without folding in any new entropy, just to generate the thing that we published in the handshake message. So it doesn't seem like there's any security difference between these two cases due to this extra HMAC, but the feeling on the list was that people are vaguely more comfortable with the extra HMAC because it looks more like TLS. So I just wanted to put this on the screen in case anyone had any other opinions, anyone wanted to express their visceral discomfort with publishing things derived off the key schedule versus publishing their MAC values. Otherwise, I think we're just going to keep the MAC until the academics tell us something one way or the other. No opinions? Thumbs up from Chris Wood. All right. That's all I got. I think it's over to Nadine from here.
Yeah, sufficient. All right, Nadine, time to talk to the microphone.
Okay, can you hear me? Is this working?
Yep.
Okay. Hi, everyone. So I'm going to be presenting about, it's not really a finished proposal, but rather something that I think might be interesting in certain parts of MLS, which is a sort of primitive or scheme that I don't think has been discussed before, even though the underlying problem has been discussed very much, I think, since the beginning. So next slide, please. All right, so the idea that I would like to talk about is hierarchical deterministic keys, or are also known as hierarchical key derivation. And this is something that we can apply to signatures in order to try to get closer to obtaining ephemeral signing in MLS. And so why is ephemeral signing interesting? Because in MLS, as in Signal, as in OTR, and essentially any mainstream secure messaging protocol, you have a long-lived signature key, and that signing key never changes. It's always assumed that if you have a compromise of the state, then that long-term identity key is going to have to be leaked. So I think that it's obvious that we cannot change the we cannot have a rotating long-term identity key. That's definitely out of the question. But I do still want to see how we can address that problem and how we can sort of try to limit the impact of long-term identity or long-term signing keys as much as possible. All right, so the idea behind HDK is essentially that if you have a private key, you can generate a public key from that private key. So here in this notation, we have a base point B. We have Alice has a secret key K. There's a public key generated from that secret key, which is just K multiplied by the base point. And then you have a random scalar X. And the idea is that if you take a signing primitive like sec P256K1, which is the one that's used in Bitcoin, then if you just add a value to the private key, and then you add the scalar multiplication of that value to the public key, then you will just get a new key pair where essentially, so this is to the right of the current slide, you'll see that there's the same value that's added to both, and then the key pair that you will receive is immediately, the secret value corresponds, the new secret value corresponds to the new public value. And this is interesting because it means that you can essentially have different parties generate new public, essentially derive new public signing keys without there having to be some kind of exchange for that new public key pair to be sent by Alice to Bob and so on. And so next slide, please. So this is already used in Bitcoin, essentially exactly the way I just described. And it's also being considered for use, if not already in use in Tor. I'm not sure what's going on there, but it's definitely been discussed. Next slide, please. But the thing is, so one potential roadblock could be that in MLS, I think that the discussion has largely been centered on maybe using ED25519 as the signing primitive. And so this doesn't obviously apply to ED25519 because it's not just naive scalar multiplication in the way that sec P256K1 is. But however, what really was encouraging to me is seeing this paper called Hierarchical Deterministic Keys over a Nonlinear Space, which essentially shows that it's possible to apply this technique to ED25519, despite ED25519 having clamping and clearing of individual bits and hashing and other things that are just not a linear scalar multiplication. So that was encouraging. So next slide, please. So this is how this would generally work. So if you just have at the top, so it's essentially a tree-like structure. And at the top, we're going to have this root signature key or a root public key. So that's KB in blue. And then from that, you can just do an HKDF with KB, but also with, sorry, if you look at the left here, you'll see that we're essentially initially generating the secret K and also the value X from, shall we say, like some some secret value W, and also the session ID of the, and this is just something I made up to explain how this works. And then from there, you can essentially derive a bunch of new subkeys that are individual different signing key pairs based on HKDFing X with the public key, with the root public key, and also a counter for each block that you're deriving. And then from that, so if you look at the leftmost child key, the leftmost green block, from there you can also derive something that is called a hardened child key. And the reason for that is that the hardened child key, shown in orange, instead of just using X, uses actually the output of the previous HKDF. So it has a higher level of sort of separation, shall we say, from the original key material. And hardened child keys have stronger security properties for reasons that I don't think are relevant right now. But if we end up using it, we want to focus on hardened child keys. Next slide, please. So I think that I've been pretty hand-wavy so far, and I want to try to bring that all together. So we know that currently in MLS, there's only one signature key, and this is the case with any secure messaging standard. And we usually use that one key for, well, we always use that one key for all the conversations, always. And if your mobile phone gets compromised, then that key is stolen, and then you can be impersonated indefinitely. And so I think that the interesting thing with HDK is that it allows us to compartmentalize signing keys per conversation, per epoch in the conversations without an additional key exchange. So I think that the improvements here are clear in case of partial state compromise. But that doesn't matter because already the initial signal-like method of dealing with identity keys is considered to be sufficient in case of partial state compromise. In fact, we never consider the danger of a signing key being compromised, except if we're talking about full state compromise, right? So far, it's not really clear what HDK can actually bring to MLS. And so I've been thinking about this, and I think that there's one way in which the additions that are possible because of HDK or the improvements can be explained. So next slide, please. All right, so let's look at the way that Signal Desktop currently does key management. And so all of the popular secure messaging applications currently essentially focus on smartphone usage for obvious reasons, because most people are texting and messaging using their smartphone, but also sometimes maybe you want to use them at work, so you have a desktop client. And so the way that Signal does this is when you're setting up your desktop client, first you have to register using your phone, but then there's a pairing mechanism, and then all of the keys are sent from your phone to your desktop client. And that includes the identity key as well as really just anything, and also all the conversation information. And so this is how it's done in Signal. And so both devices now will have your identity key. So if my phone gets compromised, I can be impersonated. And if my laptop gets compromised, I can also be impersonated indefinitely across by any device or attacker. Because it's the same exact long-term signing key pair. Next slide, please. So let's look at how WhatsApp does this. So I think that WhatsApp may be, well, I don't know this for sure, but perhaps they were aware of this concern or this trade-off, and they wanted to avoid it. So the way that WhatsApp works is that your phone still has all the keys, and WhatsApp uses the exact same protocol as Signal does. However, the phone still has all the keys, but there's like a symmetric AES link established between the phone and the computer. And the desktop is essentially just a view into the phone. So the desktop has no keys, doesn't have identity keys, doesn't even have the ratcheting keys. It just has an AES link to the phone that's established by scanning a QR code. And then it's just sending requests to the phone, please encrypt this message for me. And then the phone is forwarding the encrypted messages back to the computer. And so notice here, unlike in Signal, if you turn off your phone, you will not be able to use WhatsApp on your computer. The phone has to be turned on and connected to the internet at all times for this to work, because otherwise the computer cannot contact the phone and send any messages because all the keys are on the phone. So next slide, please. All right. So if we look at Signal, it would seem that they've decided to focus on usability. So they want it so that you can turn off your phone and you're still okay, and that's a reasonable choice. And if you look at WhatsApp, it seems that they've decided to focus on maybe security, because generally the environments in which you're executing all this secure messaging code on the desktop tends to be, from an engineering perspective, maybe more susceptible to compromise. It maybe is running in the web browser or using web runtime environments. And on phones, especially if you're using iOS, you have really good security when it comes to key management and security in general. On Android, it's different, but on iOS, it's quite secure compared to everything else. So I think that maybe what we can do with HDK is actually arrive at a better compromise when it comes to having this sort of desktop-like system, or any kind, sharing your session with a desktop, or sharing your session with any multi-device system that MLS might end up including. So as we saw in Signal, you're just sending your identity key over, and if that identity key is sent over, then if your computer gets compromised, you're done. With WhatsApp, sure, if your computer gets compromised, nothing bad happens, except maybe some plain text leakage, but you're okay. I think that maybe here, the interesting innovation with HDK is that we can essentially, from a never-changing, unchanging long-term identity key, and this is important, right? Because it simply cannot be the case that our long-term identity key ever changes. We need it to be unchanging for identification and authentication to work at all. But what we can do here is that can stay on the phone, and then the HDK root derived from that key for that conversation, or the hardened child of it, or whatever, these are details that we can come to if we decide that this is a lucrative thing to research and investigate, can actually, and only that for the existing sessions, can be transferred over to your desktop. And so what would happen in this case is that if you turn off your phone is not connected to the internet, you can still authenticate yourself for the existing chats. If you want to establish a new group chat, perhaps, yes, you will have to turn on your phone. However, for existing group chats, you will still be able to authenticate yourself. And so you have the ability to keep using your multiple devices without really having a huge risk in the way that Signal does have. And at the same time, you will have more usability in the case that your phone is offline, which is superior maybe to WhatsApp. And so this can be really good from a usability perspective, because I don't know if you guys have ever had this experience. I use WhatsApp all the time, and even if my phone is online and connected and powered on and everything, there will still sometimes be a delay because of the power management features. And so if I send a message, it'll take time to arrive because the phone needs to be woken up, and I need to open WhatsApp because it's in the background. And so all of these things will be avoided as well, I think, if we look into this mechanism. And so this was proposed on the mailing list very briefly a couple of weeks ago. Some people said that it's interesting, but there are potentially better ways of doing it. And I am very open to these better ways. We don't necessarily have to use HDK specifically, but from my perspective, the HDK was the idea that got me thinking about this. And I think that it might be interesting to, well, actually, next slide, please.
So Nadim, we got two people in line. Let's just go ahead and try to get their questions going now, if that's okay.
Well, the next slide is the conclusion. It's just 30 seconds.
Okay.
Okay.
Yeah.
There it is.
All right. So the general question, the larger question that I was asking is, to what extent can we generalize stuff like HDK in order to restrict the damage caused by state compromise, especially with regards to signing keys? And that's all. That is my presentation. Sorry if I took too long.
No, it's fine.
Thanks, Nadim. This is Daniel Kahn-Gilmore. So if you can go back one slide. So this intermediate proposal that you have is an interesting one. And I wonder about the consequences for users if they'll understand that I can have a continuation of an existing chat, but I can't start a new chat unless my phone is online. I'm wondering about the sort of usability implications there. And that led me to the question of, well, maybe you could actually, maybe the phone could send some, like a handful of not yet used HDK routes to the laptop, so that you could start a new chat, but you could maybe only start 3 or 4 or something like that. Just so the users don't typically run into this problem of like, wait, I need to message, so and so now, and I don't have an active conversation yet. But then I started thinking about that, and I'm wondering, like, well, okay, at some point the compromise of all of the routes of all of your active conversations sounds pretty bad to me. I'm not sure how it's.
It's definitely not. It's definitely not a. It's still a legitimate compromise. It's still something that is bad. I think that what I'm trying to do is to arrive at a compromise is already being used in another sense, at a middle ground between what Signal does and what WhatsApp does, because both approaches have really strong capabilities. Signal is really nice to use and fast. WhatsApp is, I guess, more secure but slow. Really, like in some cases, like 30-second delays, which are annoying in the middle of an active conversation with someone. And so I do agree that if you want to do a kind of pre-key approach and forwarding all of those keys onto the device, especially that would even exacerbate the window of compromise that you're mentioning, which is already quite serious, right? Being able to be impersonated in existing chats is a bit of a problem. But the thing is, I think that this is outweighed by how easy it becomes to recover from that compromise. Because in the past, if I lose my phone and then I want to use Signal again, I have to regenerate a new identity key, and then I have to like everyone's going to freak out. And if I'm in a security centric community, everyone's going to have to re-authenticate and check my fingerprint and so on. And so there's a sort of like large hurdle to overcome in case that happens, because the compromise is absolute.
Right.
But here, go on.
So I think what you're saying is that recovery from compromise is actually the goal here, right? Because the compromise that we're looking at in the laptop case here is basically impersonation on all of the active conversations that I have, right? And so the goal here, I think, is to provide recovery without modifying the long-term identity key.
I suppose that would have to be the case. Yes, it's also it's true that all of the active chats would not be protected by this, and therefore it does make sense to restrict the conversation to recovery from compromise. The thing is, if we look at the current MLS spec, there is some notion of epochs that's being discussed, and so perhaps, I don't know how this would affect the usability element. Perhaps it would destroy it entirely, and thus this would not be a good way to do things. But perhaps it would be interesting to see whether we could have some kind of new HDK thing happen at every epoch, and therefore the phone would have to be online at every epoch. So I don't know, maybe that would make it better, but at the same time, in that case, you will need your phone to be online intermittently. But maybe in fact that's more realistic, because in general, people's phones are indeed turned on. They're just not always connected to strong Wi-Fi, and they don't always have WhatsApp in the foreground. They do certainly have it at least once every half an hour. So perhaps that is the better way to do things.
So this sounds really interesting from a brainstorming perspective, and I don't think I want to like push further on like hashing it out at the mic, but I think this requires a lot of usability and like saying, hey, you could do this with some arbitrary schedule because we assume that people's phones will be connected at some certain times. Like, I think that's going to require quite a bit of
not some certain. Okay, so first of all, I just want to say I strongly agree, and this is why this is not like a guns blazing full proposal. This is like the title of the slideshow. It has a question mark at the end. At the same time, it's not like the devices are supposed to be online at certain times. We're talking not about a certain time, but actually an interval. So I think that expecting devices, which is like WhatsApp expects them to be online 24/7, I think expecting them to be online at least once every hour is extremely reasonable, given that it gives you these legitimately improved authentication guarantees in the event of a compromise. So that's something, but yes, this is something that I need to sit down and work out properly. But I did want to present it because I think it's interesting, and I think I will certainly have a better opportunity to work it out properly if I have your insight and feedback.
This is Mara. I don't work for WhatsApp or Signal, but from my personal experience, or if anyone works for this company, please come up. I strongly disagree with your statement that Signal choose readability while WhatsApp choose security. It's actually quite the opposite. Like WhatsApp did the simplest thing possible just to make multi-device work, which in this case is not true multi-device. However, Signal made it true multi-device, it's just sharing the same identity key. The second comment is the current draft for architecture doc assumes for multi-device world, every device is a separate endpoint with a separate identity key. So I'm not sure how this works with your proposal.
Just to be clear, I'm not really commenting on the security or superiority of any system. I'm just comparing the approaches that they do. I'm not judging. This was just colloquial feedback in order to facilitate the conversation and to make it more digestible. That being said, it is the case perhaps that in some cases, like for example, OMIMO, the specification which was created in order to facilitate multi-device signal in existing XMPP deployments, which is actually used by a software that I wrote, does indeed encourage different identity keys. And so that would be, I think, an entirely different proposal. And at the same time, different identity keys come with some complications. So you would have to essentially perhaps authenticate every device separately if you were to do that. And so because like if you look at the way that WhatsApp or Signal does it, you have these QR codes that are generated from identity keys. But in the case of multiple devices, in the deployments that I've seen of, for example, OMIMO, there is a different, hash or fingerprint or QR code for every device. And so certainly this is a potential direction to look into, but there are some complications with regards to authentication.
Hey, Nadine, this is Richard Barnes. The observation, a couple of observations here. Right now, as you may have noticed, the spec only talks about identity keys within the scope of a conversation. And so it's completely possible with MLS, you have a separate identity for every conversation. And, that's probably going to be bounded by whatever your authentication infrastructure is. If you have something, say Acme based or some highly automated authentication system, that might be feasible to have separate authenticated identities for every conversation. Whereas if you're in a manual key verification regime, like things like Signal or WhatsApp assume, you're probably going to reuse them. So I'm not sure we can say a whole lot about cross-group usage of keys. I'm not sure that cross-group usage is all that salient for MLS. So what is salient, though, is the scoping of the key within the context of a single conversation, single group. And in that sense, it's more, I'll say, linear than hierarchical. I think there's still possible applications here, but I haven't quite grokked it all the way. It might be interesting to contrast with the kind of naive approach to mitigating the risk of signing key compromise, which is to have sequential signing of identity keys, where you roll over the identity keys and have the old key sign the new key, and basically have ephemeral signatures in that way, which I think Purdue should proposed a little while ago. So it would be interesting. I don't know we need to hash it out here at the mic, but it would be interesting to be able to kind of compare and contrast that approach with the approach here based on HDK.
All right. So the best information I can go on with is that long-term keys, especially like signing long-term keys, are supposed to be long-lived. And this is based on what's currently in the architecture specification or what was discussed before, and also on how secure messengers have operated in general up until now. And so if there are potential directions in the future where we use something that's like CT or Acme or different long-term identity keys for every group session, I can't predict the future, and I haven't seen these things discussed. So when I present something like this, I have to have some axioms, some foundations, and the best foundations that I was able to come up with, the ones that seem to be the most standard and safe, is that we currently are operating in a model where we just have a long-term identity key that never changes, and how can we, proceeding from that starting point, make things better?
I think you're mixing the concept between identity key and signing keys. So the current draft for the architecture doc saying the only long term is the identity keys, For signing keys, we have a couple of modes, as I mentioned earlier, about deniability. But we always mention signing keys are changed, like per conversation. So I don't think there is mentioned somewhere in the architecture that says signing keys are long-term keys. Identity keys, yes.
Okay.
Yeah.
Well, but this would be a way to do that. So this would be a way to have long-term identity keys, but still be able to compartmentalize them, even in a fine-grained way, if necessary, to have different signatures or different signing secrets for each group conversation.
All right, we got a question from John Milken.
Hi, yeah, thanks Nadine for this proposal. So I was just wondering really how this compares against a situation where, say, every device has their own key, but when you do that, when you scan the QR code and do the relevant exchange, have the master device just sign the identity key of the new device. So you sort of effectively still have a single identity key, but other devices have revocable keys without having to actually share anything.
So that could also work. That device would be able to start new conversations on its own without querying the long-term identity key on the original device. That may come with a different set of consequences in the event of the compromise of that device, the second device, which could be weaker. I'm not sure. I can't, do a symbolic analysis right now, but it's definitely. I think that's also a good solution.
Okay, cool. Thanks.
Handshake encryption. This one, right? Yeah, okay. That one. This one. There we go.
Thanks. Yeah, like I hinted earlier, wanted to talk a little bit about general efficiency considerations in the context of MLS. So if I try to completely oversimplify what the goals are of MLS, one is to make secure messaging efficient for large groups, and we've been saying 50K is a large group. Sometimes we said 100K. And so this is what I want to focus on a little bit. So in order to measure efficiency, operations that are generally expensive, like Diffie-Hellman key agreements or signing or other things, is what we need to measure. And so if n is the group size, the number of people in a group, then some of it can be linear, some of it can be logarithmic, and sometimes we also have a constant time for operations. So with a number of current messaging systems, when you want to send out a message in a group, you encrypt it individually to every participant. You can call that PGP style in a way. So this is very expensive because it is an operation that happens at a pretty high frequency, assuming that the messaging service is actively being used. So you constantly hit the O of n line. And so one of the simplifications there is to introduce a group key, which is also known as sender key sometimes. So this makes it much more efficient to actually send a message, because initially you send out your encryption key to everybody in the group, and then they know it, and you can encrypt further messages under that key, and only do it once and not for everyone anymore. But you still have peaks that are very inefficient and linear in the group size with such a system, and you also have some security trade-offs. So the question is, how is MLS better in terms of efficiency? And so one thing that was clear immediately with our proposal is that establishing a group secret is quite efficient, because if you put members in a tree, then that becomes logarithmic. But the question is, are there other operations that are not logarithmic, and what are those, and what's left? So just want to give a brief overview of that. And so TreeChem actually solved the problem, as we discussed earlier, for adding and removing people. So when you remove them, you can blank a direct path, and generally that is still logarithmic, although there is a certain overhead now, but it's certainly not linear, other than in edge cases. And adding is the same, particularly when you warm up the tree, as we discussed earlier. So that is then roughly logarithmic as well. So what, one way to basically understand what efficiency means is that operations that are costly should be in log of n. And if we don't manage to do that, then essentially we have a peak at the end of the day in the user experience, which is not great. So this is maybe how MLS is going to work most of the time. So once in a while, there's going to be a group operation in O of log n, at least for the creator, and that can be processed on the recipient side in constant time. Actually, messages are encrypted in constant time, decrypted in constant time as well. So if we can get everything to look like that, that would be the ideal solution in terms of efficiency. And so, as I mentioned already, so for the group creation, we've made it sort of logarithmic now, but we still have two scenarios where it is linear, and they're sort of correlated. So one is when you invite a member, and the other one is when you add a device, if you run MLS in a multi-device context. So when you invite a member, you create a welcome handshake message, which contains all of the tree and all of the roster, because the spec says that every participant should have a complete view of the tree, and that goes into the key schedule. So everybody needs it. And so this is directly sent from one member to another as part of the welcome message. And when you add a device, so this is not particularly well lined out in the spec right now, but one way could be that you transfer all of the state from one device to another, which requires some sort of device pairing mechanism. The other one would be that we use something that was initially in the spec, which was user add, where a user or device can request to become the member of a group. But then we are left in the same situation as with inviting a member. That device still needs all of the state, and someone from the group has to send that to the device somehow. So this is absolutely linear, and so just to give you an idea.
Raphael, I just wanted to clarify real quick. The cost we're talking about here is data transfer costs, not DH operations.
Yeah, that's correct. Yeah. So
can I just ask on the previous slide here, for device add, it sounds like you're talking here in a situation where we are assuming separate identities per device. And we're treating the device add in that context. Because there is another approach which says that a device add by a given user is simply reflected to the group as a refresh, right? You run TreeChem for your own devices, and then adding a device just means that you change your node, and then you push that.
That's true. So there
are other ways to optimize off adding a device case.
Yes and no. So I mean, that is true. You can basically mask how many devices you have to the rest of the group by having just one leaf, And under that leaf, you have like your own private tree of devices,
Yeah.
and then you just do the update. But that doesn't fully solve the problem in the sense that the new device still needs some state, needs to get it from somewhere. It needs at least the public keys of the tree. It needs its own private leaf key.
Sure, but that's transfer between the user's own devices and not transfer out to the entire.
Yeah, sure. It's not broadcasted to the group, of course.
Yeah.
Because why would you do that? But it needs to be transferred between the two users if you assume that you have some sort of device pairing process. If you don't have that, and most systems currently don't have that, if you basically log into a device and want to connect that to your MLS account, then that device needs to get the state from somewhere. So if your current devices are not around, or you lost them all, or whatever, it really needs to get the state from somewhere.
Okay.
And as Richard pointed out, this is clearly a question of payload. It is, in this case, it is not a question of computational resources. So currently, the welcome handshake message, as it is defined in the spec, grows rather quickly. So for a group of 50,000, it's almost 5 megabytes. So right now, when you want to invite someone to a group of 50,000 people, you have to upload 5 megabytes from your phone or whatever device you're using, and the other person has to download that. So this is very far from the efficiency we have achieved with all other operations. And in the context of adding a device, the payload per conversation is basically a welcome handshake message. So you can multiply that by the number of conversations you have on your device. So if they're small, it doesn't matter too much, but if you have a number of large ones, this could be, tens of megabytes at least.
Thank you, Doug. So, it sounds like this chart is just showing that the welcome handshake is linear in the number of group messages. And, to some extent, we had already accepted that there was going to be a linear amount of state in terms of the roster and the identity keys and whatnot. And so it's a little bit unclear to me how worried exactly we need to be about this, because there is this sort of unavoidable linear cost. And yes, you can argue about the constant factor, but it's still just the constant factor.
Yeah, one aspect of this is to actually make it clear that this exists. And then Richard later is gonna talk a bit about potential solutions. So yeah, that's the slide, by the way. So the question is, can the tree and the roster be sent out of band somehow? And could the server be this out of band channel and assist with storing at least some of the tree? Yeah, and I guess that is the handover to Richard.
So yeah, to the point that was made earlier, I think that there is inevitably a new node joining the conversation is going to have to download linear state. And the question here is whether the entity adding that node should have to upload linear state, or whether the server can kind of glean and maintain a copy of it on its own. So yeah, to recap those two questions, and these reflect as different changes to the spec as well. First question is allowing out-of-band roster/tree distribution to keep the welcome message small, and the second thing is to possibly allow the server to see stuff. Yeah, TPG.
So just with regards to question one, when it says, should we allow, can we prevent?
So right now, the welcome message, the only way you can, the spec defines to tell someone to give the new member their state for the group is to send it all in this welcome message that has everything.
Sure,
So I think,
and the current mechanism for getting that to the new user is through the distribution server, right?
Right.
but there's nothing in the spec that says it can only pass through the distribution server. It's just that that's the typical way that you get data.
That's correct.
So this question
well,
of like, should we allow out-of-band transfer seems odd to me.
Actually, I think it's a little more important than that, in that if we assume that the welcome message, that the information here is that these commitments here are what. Sorry, let me just summarize the slide. The proposal here in protocol terms is to take the roster and tree, and instead of having those by value in the commitment, just put in the welcome message, just put a commitment to those things. So if these things, the hashes of the commitments to those parts of the state are what go in the group state object, probably should have shown the group state here instead. Oh well. If those commitments are what go into the group state, which is what goes into the key schedule, then the new member can join the group and compute the current group keys just by having this constant size object and not downloading the whole linear size state immediately. He only needs that linear size stuff to process the next message that comes along, or the next handshake message. So he can, do messages, application messages all day long. But he only needs the linear stuff when an update or a remove or an add comes through.
Or when he wants to actually review who he's sending messages to.
Well, yeah. Okay. So yeah, it's kind of a lazy join. You can, and he could, download that stuff. It doesn't block his entry into the group and his ability to read messages that are being sent to him in particular. I think this is probably a good idea just because it maintains looser coupling. It would allow out-of-band distribution in cases like Raphael proposes, and we could also define some in-band stuff, just like roster and tree messages to hand this stuff in-band if people want to have a mechanism defined here.
So again, just for terminology's clarification, it sounds to me like you're saying out of order, actually, not out of band. Because what you're proposing here is lazy evaluation of the tree state, right? And so whether it's in band or out of band isn't the question. The question is whether you need to have the state in order to get into the game here.
Yeah, that's fair enough.
Okay.
Yeah, because I think the spec change would be to replace these values in the welcome message, also replace them in the group state. So right now we have a transcript hash in the group state. We would also have roster and tree hashes instead of the things by value, so that you could join the key schedule without having the linear size state. Yeah, Raphael.
Yeah, maybe to add to that. So, I mean, right now you need a view of the whole tree for the group state, but if we replace that with hashes, that could still work. So the situations where you need certain elements of the tree is when you want to remove someone or, and actually that's it right now.
Well, you need your own copath if you want to update.
Right, yeah. So, but I mean, this is something that you could do at a later point in time, clearly, to address the out of order thing. Yeah.
Yeah.
So restate what I think my understanding is in order to just send messages, all you need is the root. In order to process updates, you need your own path. In order to send updates, you need your own copath. Is that correct?
Correct.
And so only time you need a list of the people, but you don't necessarily need this whole state of the tree.
Well, it's actually slightly worse than that. In that when you receive an update, you need to update the tree hash that you have, which means, depending on how we construct that hash, you might need to have the whole tree. Like if you're just taking a hash of a representation of the tree, then you need to update the relevant stuff.
I mean, I'd assume that was computed as a Merkle tree.
It is not. We haven't defined anything, but even if it were a Merkle tree, you need to have the right slice.
Wouldn't you probably need your copath again?
Not if I'm processing. No, I'm imagining a case where I'm processing Imad's update, in which case I would need his copath in the Merkle tree.
So I think
these things can be designed, but it gets to be a lot more complicated.
I think it'd be
you don't just assume people have the whole state.
I think it'd be useful to lay out, for each operation, which subset of the tree you need, and which pieces of those are specific to you or specific to other people.
Yeah.
I mean, I mean,
You can do that. I've been trying to avoid that complexity by just assuming that people download the tree.
sure, but it seems like I mean, and that may be the case. That's what you need to do. But like, I'm going to be kind of like a sad person if when I get added to the tree, like I can't do anything at all, including receive messages, until I've received like 5 megabytes of data. Like, I mean, like not like very thrilled about that. You know, I mean, yeah. So I think, you know, like, I'm all for reducing complexity, but I think it'd be, I guess, like, maybe we can create some complexity now and reduce complexity later, which is maybe we can actually work out what the answer to these questions is, and then see like if there's a sweet spot.
Yeah. Okay. Fair enough.
Jonathan Hoyt. So a lazy client could just repeatedly download the hashes from the server and never ever compute who he's talking to, if he so wished. Assuming they're publishing the server.
Yeah. And you know, one thing you could imagine is just like sending out the updated hashes in the handshake messages. And then, you know, a responsible client could download the state from the server and verify that the hashes are right. But lazy clients could just believe what the other members tell them.
So in practice, no one will ever verify any conversations, and it will just end up to... Yeah, exactly.
All right, so I'll take the action point from Ecker there to like go through the analysis and see, you know, if we can come up with a hashing scheme that can be selectively updated for the operations. Okay, this is perhaps the more interesting question. So I think the model Raphael was positing is that the server, you know, in order to avoid this need to upload linear state when you add someone, you could have the server just watch messages go by. And where this comes into tension is we've discussed often on this idea of encrypting the handshake messages as they transit the server to hide things like the state of the tree, the membership of the group. In order to, you know, enable the server to maintain a cache of the roster, you would need to expose to that to the server the stuff that goes in the roster, so the identities of the people in the group and their credentials. Likewise, if the server is going to cache the tree, you need to expose the public keys and the indices you're operating on. If you do that, there's not a whole, if you expose, so you know, the stuff that's in colors here is the stuff that you need to expose to make that caching effective. The upshot of it is if you expose all that stuff, and there's not a lot left in the handshake messages to protect. So it may not be worthwhile even pondering any sort of handshake encryption if we want to allow the servers to cache all this stuff. So that's kind of the question, like where do people, so what we're exposing here is mainly public keys in terms of the content, the amount of the handshake message. That part doesn't, to me, seem all that controversial because it's just public keys. Public keys are public. But what's more concerning here is perhaps the credentials that would expose the identities involved in the group. But even there, I think that some folks have pointed out that the server has to, in most deployment scenarios now, the server has to have some idea of who he's delivering messages to, and thus has an idea of the roster already. So, Imad.
Same with Amara. I'm all in for storing some information for the server. It's not clear to me if the server caches this information, how it keeps it up to date. If it's a client pushing the update to the server, or the server proactively reconstructing the tree by observing the add and remove operation.
Yeah, I think the idea is that the server would have a copy of the tree and would read the handshake messages and perform the updates, the corresponding updates to the tree.
This is DKG. So I think that just throwing in the towel on metadata protection at this stage of the game is premature, and I would be pretty sad if we decided to do that. And I think that's what the no handshake encryption, publish all the identifiers to the server basically means, is just punting on metadata protection. I will acknowledge that I'm not convinced that, so the way this was presented was basically like, look at these huge groups, look how expensive they are to join. And I'd be pretty sad if this meant that MLS in a non-huge group lost all metadata protection simply because we expect to lose all metadata protection for large groups, right? it's true, I don't actually care that much about metadata protection for a group with 100,000 people in it, like, because probably it's all exposed to all 100,000 of those people, and those 100,000 people, one of them is going to leak that metadata list somewhere. But if you tell me that a group of 12 people or a group of 100 people who are using MLS to communicate are going to have that group membership directly leaked by the handshake message to the server, that would make me sad. So where it says 2 modes, I would hope that if we define this, we're not talking about, your MLS deployment should offer mode A or mode B, but we should talk about what is the reasonable cutoff where a group converts from the order N mode to the order 1 mode, right? So that small groups can continue to have like the better protections.
So, Martin Thompson, are there any circumstances in which one of these messages might be rejected by endpoints? And is the server going to be able to see that?
Yeah, we discussed that some. I think that it is possible that endpoints will reject messages. I think my initial reaction to that was, you could have some knack scheme where, you could just provide feedback to the server and say, never mind that one. But to be sure, there are, issues with maintaining consistency.
I assume in that case, the server doesn't need to see, you're saying the server needs to see the NACs. Couldn't you also simply say that if the server sees another message with the prior epoch, the same, it backs the last one out and puts the new one in?
So, like there are ways to do it, but you would need to have some consistency mechanism. Yeah.
Yeah, coming back to your point, so I fully agree that it is a bit harsh to basically get rid of the privacy we had around handshake messages just to support very large groups. So I think it could be a model where this is entirely optional, and we keep on encrypting, or we go towards encrypting handshake messages and having a very opaque modus operandi. The other question is how much identifiable information does the server really see with that? Because there's like various degrees of metadata. So there's the public keys in the inner node of the trees, which you cannot really correlate. At least right now, I cannot think how you could correlate them to anything. But then the credentials is something different. So they're potentially, I think the idea, Richard, was that we would only expose part of the credentials, and that's why they're in blue here. So in the user init key, you would only expose the Diffie-Hellman key of that to the server, but not the actual signature, because the server doesn't need the signature to basically cache the handshake messages. So yeah, it's not something that is quite clear in general. So we need to come up with a concrete proposal to basically take decisions. The idea for today was simply to raise awareness around the discrepancy we have between these different kinds of operations and the payload around inviting members or adding devices.
Yep, so we're out of time for today. We do have another session. We were going to kind of bump the message protection stuff down to be done on Thursday. Benjamin can't make it, but Richard said he could do the slides, and we're basically just going to recap what we did at the interims to get people up to speed.
So just to recap this, action items out of this last slot. So I'm going to plan to change the welcome messaging group state to use commitments, and then do the analysis that Ecker suggested about who needs what, how we can make that commitment updating scalable. Raphael, I'd like to assign you the action item to take a look at this question of how you might be able to do adaptable handshake message encryption to allow the server to see some stuff. Is that all right? Thanks.
Cool. And thanks, Chris, for taking notes. See y'all Thursday.